Good morning, everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Deeb. I'm a Senior Principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Dr. Andrea Leeson, followed by a list of upcoming webinars in the series. After Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's event features two presentations on DoD efforts in the area of environmental restoration. The primary topic of the webinar is the practical assessment and optimization of redox-based groundwater remediation technologies. First, Dr. Paul Tretniak from the Oregon Health and Science University will provide some background on traditional redox measurement methodologies, as well as advantages and challenges of using alternative approaches. His presentation will be followed by a short Q&A session. Second, Dr. Richard Johnson, also from the Oregon Health and Science University, will discuss redox applications in detail with a focus on two case studies. His presentation will also be followed by a Q&A session. We will conclude the webinar with an interactive Q&A session involving both our speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions in advance of that session. On this slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of the screen. With that, I would like to introduce Dr. Andrea Leeson, who is both the Deputy Director of SERDP and ESTCP and the Program Manager for Environmental Restoration. Andrea has been with SERDP and ESTCP since 2001, and before that, she was a research scientist at Battelle Memorial Institute, where she conducted research on in situ bioremediation. With that, I turn it over to you, Andrea.
Thanks, Rula, and welcome everyone to our webinar today. For those of you not familiar with our program, I'd like to give you just a little overview of our two programs. SERDP is the Strategic Environmental Research and Development Program and was established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately is intended to impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental as well as energy technologies. And these investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of the SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are mostly at the pilot and field scale, although occasionally supporting lab efforts are conducted. We have 4 program areas in SERDP, 5 in ESTCP. The Energy and Water Program area is the only one in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Climate Change, and Weapons System and Platforms, are SERDP and ESTCP programs, and they're managed jointly by a specific program manager. Our webinar today is focused on research and demonstrations that were conducted under the Environmental Restoration Program area, And we have essentially 5 main areas under environmental restoration. We cover contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, as well as risk assessment. Our webinar series will be highlighting research and demonstration efforts from each of the 5 program areas, and listed here are some of the upcoming webinars. As you can see, they cover a broad range of topics, and registration is now live for each of these webinars. In November, we'll have another webinar based on research and demonstrations done under the Environmental Restoration Program area, and that webinar is going to focus on bioavailability issues. You can find more information about our upcoming webinars on our SERDP and ESTCP website, and I hope you enjoy the webinar today. Rula?
Thank you, Andrea. It is now my pleasure to introduce our first speaker, Dr. Paul Tretniak. Paul is a professor in the Institute of Environmental Health at the Oregon Health and Science University. His research interests are associated with a wide range of oxidation reduction reactions that occur in the environment and the contribution of these reactions to the fate of organic pollutants. Paul is the principal investigator on several past and ongoing projects funded by SERDP related to aspects of abiotic natural attenuation, in situ chemical reduction, in situ chemical oxidation, and redox characterization. Paul, please proceed.
Thank you, Rula, and thank you, Andrea, for the opportunity to talk to so many of you today. I'll be describing the initial background part of the project that we just recently completed that was funded by SERDP that has the same name as this webinar. A lot of what we'll be telling you, however, is related to work that we are continuing to do on several other new SERDP projects. So this will be the first step in hopefully what will become a series of advances in this area. So my part of the presentation is background and challenges, and so I'm going to start by talking about the limitations to traditional methods for characterizing redox conditions. I'll introduce this idea of chemical probes, and in particular I'll describe what we're calling CRPs, or chemical redox or chemical reactivity probes. And I'll describe how we go about selecting those probes and what criteria we use, etc. Then I'll illustrate some results on using those probes to characterize the redox properties of minerals, and then show you how they compare to more traditional measurements that are made using a platinum redox potential electrode of the conventional commercial sort. And then in the end, I'll talk a little bit about what this tells us about contaminant reduction rates. So the starting point for this project was framed in order to try to make it as big as possible in terms of its implications to remediation practice in general. So we started out with this rather bold notion that almost all approaches to remediation of groundwater contamination involve oxidation reduction reactions, so redox reactions. And so I diagram that with this little cartoon where I show techniques in red, for example, in situ chemical oxidation, ISCO, and in situ chemical reduction, and ISCR. Those are obviously redox-based technologies. The three in the orange are more or less biotic processes that involve metabolic contaminant degradation pathways. If you think about that, those also turn out to be primarily redox processes. And even something like in situ thermal treatment, which is up at the top there, which you might think of as being primarily a sort of a physical treatment scenario, turns out to involve to some degree a certain amount of chemical degradation by redox processes. So what we're doing here has broad application to a wide range of different treatment approaches. However, the problem that cuts across all of this is that the criteria, the techniques that are available for assessing the conditions and the effects of treatment with respect to redox conditions have proven to be problematic over the years. So the techniques that people typically use are platinum electrode potential measurements, which I've mentioned just a minute ago. Here I'm also pointing out that term, that's often called an ORP for oxidation reduction potential. So platinum electrode potential measurement, ORP measurement, it's the same thing for our purposes here today. Or another criteria that you probably are familiar with, which is the idea of a natural oxidant demand, which often goes by NOD. Those kinds of things are out there and they're being used, but they have proven to be not entirely adequate for characterizing real sites and predicting real remedial outcomes. So in particular, the problem of selecting between alternative technologies, the problem of optimizing the implementation of any particular selected technology, or assessing the performance of any particular technology that's been implemented. So if we're going to try to do better, the first thing we need to do is be clear about exactly what we're talking about. And early on, it became apparent that we needed to divide this problem up into three parts. And so this slide defines those three parts, and the Venn diagram is there to try to convey the relationship between the three parts. So there's the thermodynamic element here, which is the question of will the reaction occur at all. So the reaction has to be thermodynamically favorable to happen, and in redox processes that is sometimes true and sometimes not true, and so therefore that has to be addressed sort of primarily. But even if the reaction is thermodynamically favorable, it may or may not be kinetically significant. And so then the question is, how will it be fast enough to do the job that needs to be accomplished? So that's the kinetic criteria. And then the last one is what we're calling the capacity criteria, for lack of a really conventional term there. And the issue there is, will it go far enough? So it may occur, it may go fast, but if it doesn't go all the way, then you haven't met your treatment goals. The Venn diagram is meant to show that there is overlap between these things, and that's okay. You might use it as a little exercise for yourself when this is over to try to figure out why I drew the overlapping spheres exactly the way I did. I think we did it right, but it takes a little thought to decide how they should go together. All right, so now for all of my presentation, I'm going to focus on the thermodynamic part, so the first one of those criteria. Rick's part of this presentation the emphasis will shift more towards the kinetic and capacity aspects of this problem. So as I've pointed out previously, typically what people do is they measure platinum electrode potential measurement, or EH, that's here, or this other term here, ORP, and that's something that probably all of you are familiar with doing. Alternative things that are sometimes used are DO measurements, measurements of other terminal electron accepting processes, like nitrate, sulfate, etc., or measurement of dissolved oxygen concentration, or sorry, dissolved hydrogen concentrations, which is a kind of a slightly different issue that we're really not going to get into here, but it's closely related. When people do that, they typically end up with a number like an EH, and they may plot that versus pH in the format that's shown in this figure on the lower right. And this is a classic thing to do. This is an EH-pH diagram or a Porbet diagram. And the idea is that these two variables are the master variables that sort of control the overall chemical conditions in the system more than anything else. And so you can represent natural water conditions in this EH-pH space, and that's what's shown in this figure. And I've highlighted in red a kind of a qualitative classification of different water conditions that was put together many years ago by some geochemists. This is my version of a classic very old figure that you can track down using the reference at the bottom of this slide. However, the problem is that when you look at this kind of formulation carefully, you realize that there's a lot of inconsistencies start to come up. And to really drive that point home, I've resurrected another very old figure here that you should all know, because this is a really classic figure in representation of this problem. It comes from a PhD thesis by a guy named Lindbergh in 1984. The version I'm showing you was adapted from the geochemistry textbook by Langmuir in 1997. What they did is they took geochemical data from a lot of water samples that was in the old U.S. geological database called STORET, and they compiled it in this figure. And they used those numbers for all the redox active species like sulfate, sulfide, nitrite, nitrate, nitrite, etc. And they plugged those into the Nernst equation to calculate what the corresponding EH would be. And so here they calculate the EH number here using all these redox couples over here based on chemical speciation data that was in the STORET database. And they plot it versus the field measured values of EH that were obtained with the platinum electrode. Now, if this was working the way it's supposed to, everything would fall on that diagonal line. Obviously, it doesn't do anything remotely like that. And so what this figure shows is that all these species in natural waters are not in equilibrium. And so the idea that you can make one platinum electrode potential measurement to get this EH number, and it's going to tell you anything about all of these chemical species in that water, is really not going to work. And so that's an illustration of how fundamental this problem is. Now, to explain why that's the case, I developed this slide a little while ago. This really shows the fundamental problem. So you have this electrode, and the electrode is in contact with a variety of these redox active species in water, and each one of those has a redox couple that goes with it. And each one of those redox couples corresponds to a Nernst equation down here, where this is the reduced and oxidized form of those species in each couple. And you've got a bunch of those for all the different redox couples. And they are weighted by their sensitivity to the electrode, which is this red term. You sum them all up, and then you get this total measured mixed potential for the system. And so now the problem here is that all of these couples are not in equilibrium. And so each of the contributing terms, they don't match up. And it occurred to me that there's actually a timely analogy that might help you remember this slide, which comes from the ongoing, say, presidential election. So when they do public opinion polling of the overall favorability of, say, Congress or the president or any particular presidential candidate, they give you a number, right? But the number reflects opinions of, say, people in Portland and people in Dallas, Texas, and those two groups of people are not in equilibrium. And so you get a net result, which is that favorability is is good or bad, but it doesn't give you any really actionable information about the individual components that make that up. So it's actually quite a good analogy to illustrate how this equation really works. So now there's one other key fundamental aspect of this that I want to mention before I move to the sort of project specifics, and that is the idea that a lot of what the platinum electrode potential measurement measures is just what goes on in solution. It's solution chemistry that it sees, because only the water really is contacting the electrode surface. We know that what's most important in a groundwater situation, or in a sediment situation for that matter, is the surfaces. It's the minerals, it's the solid phase, it's the particulate organic matter that's really the most important actor in the redox process. And so if you want to get an accurate measure of redox conditions, you somehow have to contact those surfaces. And so this slide here illustrates a demonstration that we did using some of the techniques that I'll explain more fully in just a moment. And we posted this as a video, actually, that you can see on the SERDP website. It's in their blog. The URL for the blog is down here. I think you can also find it on YouTube if you dig around a little bit. And the idea here is that we used a redox indicator dye. It's the dye is called Resazarin. I'll say more about this in just a minute, but for the moment, you just need to know that it's purple when it's oxidized, it's pink when it's reduced. And so what we did is we put it in a syringe in this solution that's just about the right amount of concentration so that you can see the color well. And that we connected to a column that contained porous medium that we had collected from a sample site. And then we withdrew water from the inside of that column that had equilibrated with that mineral material, and we withdrew it into the syringe, which is what you see here. And what you see in this middle image is just that the blue color gets diluted out. So there's really apparently no redox going on with the dye. But then in the last frame, what we did is we pushed that solution back into the column and then pulled it back out again. So now that the blue dye has had direct contact with the minerals, and when it comes out pink. It comes out reduced. And so it's a very dramatic demonstration of the fact that all that's important in this system is happening on the surfaces, and that sampling the aqueous phase alone doesn't really tell you what you need to know. All right, so on to the project. Now we have objectives for the project that just finished, ER2308. Our overall goal was to demonstrate a better way to do this, and we had specific objectives which included reevaluating the old techniques, developing this new technique, this probe technique, and then quantifying the relationship between them. The approach that we're taking here is based on a paradigm that's represented by this cartoon and this figure here. The idea is that when you have a contaminant that's being, say, reduced in a subsurface medium, that would be this, in this figure here, we're calling that contaminant of concern, COC. We're going to use, say, TAC perhaps as an example. And that's this black line here in the bottom part of this figure. And what it's doing, the idea here is that the contaminant is reduced or degraded at rates that depend on the components of the groundwater system, say various abiotic reductants, biotic reductants here, mineral materials, magnetic minerals like magnetite, etc. And that this squiggly black line represents a sort of a response curve to the overall degradation of the contaminant under those conditions. The problem is that that's often too slow to measure, and then it's very difficult to get an assay like something like say magnetic susceptibility only tells you about this part. It doesn't tell you about, say, this part or this part. So we're looking for a probe that's more broad in its response. And so what the idea is that we're going to use a chemical probe, and we're going to add the chemical probe to the system, and it's going to have the response that corresponds to, say, that blue line. And to the extent to which the blue line is parallel with a black line, then we can correlate those two, and we can give a much more rigorous characterization of the potential degradation of the contaminant. So that's kind of the concept behind how we're trying to approach this. We got to have some probes to do this with, and so it turns out that there's a history for this kind of thing. And so in this figure here, this table is an old work study that I did a long time ago, where I evaluated 6 of these different potential probe type compounds using reducing sediments, and showed that they have some useful properties. This figure down here is a new one from the René Schwarzenbach's group in Switzerland, where they're doing a similar kind of thing using a different suite of probe-like chemical compounds. And so for this project, we went through a bunch of them and evaluated their pros and cons. And we came up with this list of 4 that are our primary candidates for the time being. And for the purposes of this presentation, we're really only talking about 2 of them. The top one, this resurfin couple family of indicators, and the second one, the indigo sulfonate family of indicators. So just very briefly, a little bit of background on these, and the first 2 of them. The resurfin family is shown in this slide here. So this is the structure of resurfin. It's the one that's pink. Its parent compound is this purple compound. That's the fully oxidized form. There is a fully reduced form that's colorless that's over here on the right side of this set of reactions. The chemistry of this compound is very well characterized. It's widely used for lots of things, including a lot of microbiological assays. What I'm showing down here is just an image from a cell viability assay, commercially available, widely used. The point of showing that is to convince you that these chemicals are not toxic. So if one wanted to inject them into the ground, for that matter, say in the form of a push-pull test or something, it's conceivable that one could do that. The main thing we're interested in here is that we can measure the color quantitatively, and we can convert that into numbers like kinetics or equilibrium constants, EHs, using this essentially as a quantitative colorimetric indicator. The other family that I want to introduce is the indigo sulfonates. The prototypical compound there is indigo disulfonate. That's this blue one, and its reduced form is this yellow form structure that's shown over here. This figure down here shows the conversion, the reduction of the blue to the yellow by reducing sediment, which is at the pellet at the bottom of those tubes, and you can see that the color change is unmistakable, so that's a nice property of this particular material. And it behaves very nicely in spectrophotometry, and therefore we can do lots of quantitative things with it. Again, the question would be, is this something you could ever use under environmental conditions? And this compound is basically what you dye blue jeans with. So if it was toxic to humans, you would know it by now. So we think it's probably a viable choice if somebody wanted to try to apply it in the field. So now what we're trying to do here is use this quantitatively. So what we're going to do is we're going to measure the concentration of the oxidized and reduced forms. And so it'll be oxidized form and reduced form here. We're going to plug them into the Nernst equation here. We're going to add in all these other constants that we know from the literature, and we're going to calculate this number we're going to call ECRP for the reduction potential calculated using the CRP probe compound. And we did that in a whole series of studies, and the one that I'm going to feature in the last couple of slides here is this one. This is a new paper in Environmental Science and Technology. And if you want to get copies of this from us, you can email us, or SERDP will facilitate getting copies of this. You can use the DOI that's shown here on this slide. We did a number of things in this particular study, and I'm going to quickly go through those now. One of them was to measure ECRPs using samples of a bunch of different reducing mineral type materials that are relevant as models for what you might find in groundwater conditions. And we varied details like pH and concentrations, et cetera. And so we end up with these families of little colored lines here. And so we did lots of measurements, and we compared those to literature values and showed in the paper that this was giving promising results. Now, the result that's probably most interesting to many of you here would be shown in this figure here. So what we've done is we've taken the chemical redox probe technique and used that to get ECRP, and we're plotted it down here. And in the same experiment, we've used a conventional platinum electrode, and we've used it to measure the number that's on the y-axis. We plotted one versus the other. And initially, the first version of that result, you get the red dots. And as you can see, the red dots fall well above the 1-to-1 line that would be agreement. And so what that shows you is the platinum electrode potential measurement is too high. And it's too high because it's not seeing the reducing mineral surfaces. Instead, if we add to the solution, we add a little bit of the CRP type compound to each bottle, the red points move down to the blue points. Basically, they fall onto the 1-to-1 line. So what this shows is that the CRP solves part of the problem with the platinum electrode potential measurement, and it allows you to get a more meaningful number using the platinum electrode potential or measurement. And Rick will illustrate that in his slides. So then the other thing we want to do, which is kind of getting to the punchline for all of you that are mostly concerned with cleaning up sites, is to try to show whether there's a relationship between this ECRP number that we now showed you how to measure and contaminant degradation rates. In this case, the y-axis is K observed for disappearance of contaminants in a batch experiment. We used 3 contaminants for this particular study. We can talk later about why we picked these particular 3, but the point, for the purposes of this slide, the thing to see is that the green line is a nitroaromatic compound, so something like an explosive TNT RDX family of compounds. The red line is a chlorinated aliphatic, and the blue line is another perchlorinated aliphatic compound, carbon tet. And clearly the nitroaromatic goes faster, the chlorinated compounds go slower, but the most important thing here is that there is a pretty good trend between the correlation between our ECRPs and the observed rates of degradation. And that's ultimately where we'd like to get. We'd like to be able to have you be able to say, make a measurement of this number and then essentially use that red line as a correlation. That's what I'm referring to here as a QSAR. And use that to estimate what the degradation rate would be off the y-axis. So now the last slide here shows what happens if we extend that to the available data that's in literature for a wider range of compounds. And what you see is that if we plot the rate constant for contaminant degradation on the y versus our different reducing mineral phases on the x-axis, we get relationships that follow these diagonal lines. What's on the x-axis here is not exactly the same as what was on the x-axis in the previous slide, but the latter is derived from the former. So for this one is an outcome of that ECRP measurement. So what you see is that up here in the top, the green diagonal zone band is nitroaromatics. Again, they're the fastest by far. The blue set here are chlorinated aliphatics like carbon tet and hexachloroethane. They're in the middle, moderately fast. And this reddish group down here below is the chlorinated ethenes, TCE and PCE. That qualitative trend is not surprising. The diagonal bands that we've drawn are a little bit dubious in the sense of they're not fitted at this point, but that's where we would like to be able to take them. And the final point to make from this particular image is that you'll notice that there's a great big gap down here where there are really no numbers, and that would be chlorinated ethenes like TCE being reduced by iron 2 containing mineral phases like iron 2 on hematite or lepidocrosite. That's exactly the kind of conditions that probably are most relevant to abiotic natural attenuation scenarios, and there's a great big data gap. But what we know from ongoing work, including some work that's funded by SERDP that's going on right now, the data that people are starting to get on that particular problem is probably going to fall right in there where this particular figure would predict that it should. So with that, I will just quickly summarize and say that the starting point of this was the problem of redox assessment. Almost all redox remediation is redox-based. The methods for characterization of those conditions are not really adequate, and we need to cover thermodynamic and kinetic aspects when we do that. To improve on this, we need an alternative approach, and we've explored this thing that we're calling chemical redox or reactivity probes, CRPs. I described two of them in some detail, the rosazurin and indigo disulfonate families, and showed you that they give pretty complementary results. And then the specific results that I showed that come from the paper that I featured at the end there showed that we can use the Nernst equation to calculate a redox potential using the CRP data, that we can make ORP measurements in the conventional way. We can make them match. We can show that there's a correlation to contaminant degradation rates, and that we can even use that to rank different regimes in terms of their likely rates of contaminant degradation. So with that, I'm done, and I will take questions for the little bit of time that I have left.
Great. Thank you so much, Paul. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions on the first presentation that Paul will answer, and I'll start with the first one. How many of these chemical probes or CRPs have already been used in contaminant hydrology applications, Paul?
So in developing this project and in evaluating and selecting probes, we certainly paid careful attention to precedent, because we want to be doing things that the practitioner community can easily adapt to. So if any of these had been used previously for anything, that would be relevant. There are two things in particular that are examples of how this already has been done. The one that's slightly less compelling in this context is that there's a large history of limnology type people using the rosazurin family of indicators to assess microbial activity in sediments. And so for people that come from that background, some of this will be quite familiar. With respect to the groundwater applications, there is actually a very interesting set of papers that were done by a geologist at Oregon State University. His name is Haggerty. And in those studies, he used also the rosazurin family of compounds in large sort of porous media tank type scenarios, and I think he may have applied them even in some actual field sites, and used them to map out redox zones in plumes in porous media, et cetera. So there is already some precedent for scaling this up.
Great, thank you. Can you tell us how small-scale heterogeneity of subsurface systems may influence the performance and utility of these chemical probes?
Yeah, that's a really good question, because it's in a way it's kind of a microcosm of the whole cross-cutting issue here. So if you think back to that concept figure that I showed you earlier towards the beginning, which I described as a response curve, the microheterogeneity issue is just a part of that problem, right? So the response curve, the shape of the response curve is a function of a variety of things, including the concentrations of reductants, the types of reductants, and the availability of those reductants. And so the microheterogeneity is a problem insofar as our probe doesn't match the behavior of the contaminant. But insofar as our probe does match the behavior of the contaminant, it's actually an advantage of the CRP approach over, say, a conventional platinum electrode potential measurement, which never would have any possible hope of representing microheterogeneity.
Thank you. Also, if the water sample is already colored or turbid, does the background interfere with chemical probe determinations?
Yeah, the answer is yes and no. So over the course of the project, we evolved a little bit in our thinking about what the ideal or the most practical application of the CRPs would be. And initially, we envisioned that the measurement would be done colorimetrically. And a lot of what I presented was done sort of through that window. As we worked on this, we realized that it might make better sense to use the CRP to mediate the platinum electrode potential response, the platinum electrode response. That's the approach that Rick will emphasize in most of his presentation. And the point here being that if you use the latter, the question of color in the water goes away. If you try to do the measurement spectrophotometrically, then you do have to worry about what to do if the water has a bunch of background color.
Thank you. Can you tell us if there's a limitation or range for which these chemical probes would apply within the spectrum of redox conditions?
Yeah, that's another really good question, and we worked hard on this. So the probes have to be selected to match the redox conditions that you're characterizing fairly close. They have to be kind of in the same ballpark, and the details of what that is in our papers. So in order to do this, you need, in order to be able to cover a range of environmental conditions, you need a range of probes. And so we have so far developed and demonstrated 4 of them that covers a pretty decent range of the potentials that we need. Currently, we're struggling a little bit with the upper end, the kind of near 0 millivolt kind of range. The chemical probes that are available in that region are not quite as appealing at this point. So there is some gaps there. There's some gaps to be filled.
Thank you. can you tell us if there are any problems associated with fouling of the platinum electrodes during measurements? And are you aware of an electrode cleaning step needed between measurements?
So the answer to that question would depend a little bit on which version of this methodology you're using. So if you are going to use, say, a platinum electrode in the conventional way to measure the ORP on a water sample, then normally you would want to make sure that electrode is clean and not fouled to make the measurement. And so the hard part then becomes one of how do you do that reproducibly. In what we're doing here, we're really emphasizing the idea that the chemical probe is mediating. And so then maybe the question then becomes, does fouling of the platinum electrode become less of the issue in the presence of the CRP? And the answer is it should. We haven't shown that directly, but it should, and so it should go a long way towards alleviating that problem.
Thank you. And before we turn it over to Rick, we have about 10 questions that we didn't get to. We'll try to get to them during the final Q&A. But one last question for you, Paul. Do you think that this will ever lead to a simple method for site-specific prediction of contaminant degradation rates?
Well, maybe you left the most complicated question to last. If you think back, if you could look back to the last couple of slides I showed, where I was talking about contaminant degradation rates, you want to keep in mind that y-axis, that contaminant degradation rate number that we're using in those figures, is still a kind of a site-specific number, right? So what we're really proposing to do here mainly is provide a way to predict relative rates of reactivity. So that one site would be more faster than another, or one contaminant would be faster than another. To make predictions of absolute rates of contamination or contaminant degradation rates, one would still really need to use site-specific data.
All right. Well, thank you so much for a very compelling presentation. And we're going to turn over right now to the next part of the webinar, which will be presented by Dr. Richard Johnson. Rick is also a professor at the Oregon Health and Science University, but he's in the School of Public Health. Rick's recent research has centered on large-scale studies of groundwater contamination and diagnostic tools for characterizing in situ remediation processes. In addition, for over 20 years, Rick has worked on coupling physical and numerical models to examine the transport and fate of chemicals in the subsurface. He has extensive field experience in a range of oxidation and reduction-based in situ remediation technologies, including chemical reduction with zero-valent iron. And with that, I turn it over to you, Rick.
Thanks, Rula, and thanks, Paul, for a great background to talk about this. As you can see from the outline, what I'd like to do in this part of the webinar is to talk about a couple of examples that we have developed in the course of our SERDP work in ER 2308. I'll start off just by touching again on some of the concepts that Paul talked about to make sure that we're all on the same page. And then we'll get into these two examples. They're primarily laboratory-based, but they both have a connection to the field, and that has proved important in this project because we learned things in the field that we didn't understand before we went to the field. So we'll try to couple the laboratory and the field together in that. The examples are going to focus on nano zero-valent iron, and that was, in fact, a lot of the work that was done in the context of this sort of project. But as Paul clearly pointed out, in principle, these chemical reactivity probes are applicable over a really broad range of both in situ reduction and in situ oxidation procedures. So just again quickly, chemical reactivity probes or chemical redox probes. Paul went through the arguments for why these make sense and in fact why they can be practically used. They can be applied in a variety of ways, and I'm going to focus mostly on the kinetic and capacity aspects rather than the thermodynamic aspects that Paul talked about. They can also be used to be quite selective, so we can choose those CRPs to cover specific ranges or to look at specific processes, and in doing that, we can really learn a lot about how systems are behaving, much more than we can get from just a platinum electrode or a DO measurement, for example. And again, you've seen this figure from Paul, and the focus here will be on the kinetic and capacity sides. Again, to try to create those figures that Paul showed at the end of his talk, where we would estimate rate constants from the chemical probe data. Those are the kinds of things that we hope to be able to do. And again, in the context of that last question that Paul was asked, can we cast this in an absolute sense? We're gonna try to get to that point. The real benefit for us, I think, is to identify whether or not kinetics and capacity are likely to be met at a particular site. And also the final question about microstructure of the system. This approach, as we'll see, gives us an opportunity to really drill into small low permeability zones, for example, and look at the kinetics of those zones in ways that we just really have not been able to do in the past. Finally, again, we've talked about in-situ chemical reduction. That will be the focus of these two examples. The focus is primarily on abiotic processes in this context. However, as many of you know, the line between abiotic and microbial processes can often be blurred. The example I mentioned here is sulfate reduction to produce sulfides, and those iron sulfides can be very reactive in the subsurface. So again, another advantage of the chemical reactivity probes is that we can span the biotic and the abiotic and use those probes in ways to help us decouple what's going on. So the first example that I'd like to look at has to do with developing a field deployable approach for measuring nano zero valent iron as it's injected and transported in the subsurface. And this, of course, is a big deal, and I think you'll understand why it's a big deal even more when we finish this discussion. Nano ZVI is very reactive. The question persists as to whether or not we can deliver NZVI at any distance and have it retain its reaction capacity. And so the purpose of this work was to develop a methodology that would allow us to quickly assess what the kinetics and the capacity of zero valent iron were in the course of it being transported away from an injection location. We went for a simple technique that could be applied in the field. The method is basically based on adding a water sample containing NZVI to a solution containing these redox sensitive dyes. And so the next few slides, I'll go through one, the chemistry of that, and then two, how we implement that in a practical way in the field. So for all of this work that I'll talk about today, we're going to use one of those dyes that Paul mentioned, indigo disulfonate, that I'll abbreviate as I2S. And again, this is the blue jeans version of the dye. It exists in the blue form as oxidized, as we see here. It can react with zero valent iron, so NZVI and Fe0 will be used interchangeably in this discussion to describe that. And it results in the production of iron 3 and the reduced or yellow form of I2S. And down here we can see spectrophotometrically that we have a large peak at 610, which corresponds to visual blue look, and when we're done, we end up with no longer a 610 peak, and we have more absorption down at the 300 range, which corresponds to the yellow version. Looking at the stoichiometry of that reaction, we see that it takes it takes 1.5 moles of indigo disulfonate to reduce 1 mole of NZVI. So this reaction says that it takes two atoms of Fe0 to reduce 3 molecules of I2S. And so we're going to look for that number and use that number to back calculate how much iron 0 there would be present in a sample based on how much of the I2S we were able to convert from the oxidized to the reduced form. And because the 610 nanometer peak goes away as things are reduced, we can simply track the intensity of this 610 peak over time and get kinetic data as well as look to see how far the reaction goes to get capacity data. We tried to keep the measurement as simple as possible because we want to be able to implement it in the field. So basically, what we do is we prepare in advance a whole bunch of crimp top vials containing oxygen-free indigo disulfonate at a known concentration. We can then go into the field, inject a milliliter of sample that we collect from a well or from some other location, and track the intensity of that blue peak over time as it becomes reduced and converts to the yellow form. So the photograph on the right is intended to represent the conversion of the oxidized form of I2S to the reduced form. And again, we can track that over time and see both the rate at which that conversion takes place and the extent to which it takes place. And that's shown more clearly in the next slide. So again, the conversion from blue to yellow we track by just simply looking at the disappearance of the blue. So on the graph on the left, we see that the y-axis corresponds to absorbance at 610 nanometers. And we can track that over time and do that with different initial concentrations of zero-valent iron. And what we see is that the concentration of the zero-valent iron as represented by the amount of oxidized indigo disulfonate decreases. So that is, we react the iron 0 with the I2S. We see that reaction taking place by the disappearance of the 610 nanometer peak, and we can track that in time. And we can use these data to get a rate constant for that reduction process. And we can also use the point at which the reaction comes to a stop as a direct measure of how much zero-valent iron there was to begin with. So we can use this to build a calibration curve. We can then go out to the field and collect samples, inject them into these prepared bottles, and measure not only the kinetics, but also the extent to which the ZVI can reduce the indigo disulfonate. Of course, to have confidence that this works, we need to demonstrate that we do have a relationship between nano-ZVI and the amount reduced. So this plot takes all of our laboratory data and plots the amount of NZVI that was in the solution to begin with that we can measure by an independent technique, and the amount of reacted I2S, and plots those versus each other. And what you see here is that we get a very good correlation between those two. And in fact, the slope of that correlation line is 1.45. Theoretically, we would expect a value of 1.5, so this is quite close to that and gives us confidence that our method is, in fact, going to work well. We can take that approach then, this new tool that we have, and make a number of interesting measurements. So, for example, these are data from our laboratory where we synthesized fresh NZVI, and we put that NZVI in deoxygenated water, and the concentration of the NZVI was set to be 100 milligrams per liter, which is a pretty typical concentration that one would find delivered in a field site at a neutral pH, and we can use the CRP to track how much zero-valent iron is still around after periods of time. And what we find, much to our initial surprise and much to people's surprise these days when we present it, is that the ZVI, the nano ZVI, disappears in anoxic water extremely rapidly. So within a day, at these kinds of conditions, more than 90% of the ZVI has likely been oxidized by direct reaction with water. Nothing to do with contaminants, just the direct reaction with water. And so that means that any contaminant degradation that's going to take place has to happen in the time frame that's shorter than a day, and obviously that has a big impact on how we design these kinds of remediation systems and in fact the effectiveness of nano ZVI. We can run similar experiments with TCE as a function of time, and what we see when we react zero-valent iron with TCE is that initially we get reaction rates that are relatively rapid, as evidenced by the decrease in TCE concentration. But after a couple of days, things come to a complete stop and never change again. And the reason for that is that all of the zero-valent iron has already been consumed by reaction with water, and therefore it's not available. So the TCE data confirm what the CRP data told us, that in fact we don't have long for the TCE reaction to take place before it's all gone because the ZVI has been oxidized by the water. We can confirm that with a separate set of experiments in which we look at the production of hydrogen gas. The reaction that you see at the top here is the standard reaction with water, ZVI, because water is unstable in the presence of ZVI, water breaks down and yields hydrogen gas, and so we can look at the evolution of hydrogen gas to tell us how fast this reaction is taking place. And so these data show, again, laboratory measurements of the production of hydrogen, and what is a little harder to get out of this directly is that essentially all of the available ZVI is burned up in 2 days, and that's shown by basically this plateau, and the theoretical value for how much zero-valent iron there was based on how much hydrogen we would produce is shown over here in the solid blue dot. So basically we burn up all the ZVI in 48 hours, and the capacity is then gone. This has led us to think about other ways that we can minimize this serious problem, because under the kinds of conditions that we were describing here, the water reaction dominates over the TCE reaction, and more than 95% of those conditions of the zero-valent iron goes to the reaction with water, and only 5% is able to be used for the reduction of TCE. So we'd like to change this number to try to get an improved yield of TCE. And one of the standard ways of doing that that we have been developing over the last few years, and that others are doing as well, is to treat the nano ZVI with a sulfur-containing chemical that would create a surface coating of iron sulfide, and that iron sulfide is much less likely to react with the water, but it still retains reactivity towards the contaminants. So the first place that we took this chemical reactivity probe technique to was a field injection of nano ZVI that took place in Ontario, Canada, and it was orchestrated by Dennis O'Carroll and his colleagues at the University of Western Ontario. There they synthesized the same kind of NZVI we use, but right before they injected it, they treated it with sodium dicyanide, again to produce a sulfide coating on the nanoparticles that would hopefully reduce its reactivity with water while retaining its reactivity towards the contaminants that were present at that site. And our role in that operation was to essentially assess the reduction kinetics and the capacity from water samples that were collected during the injection process. Again, we use that same technique because it's easy to accomplish in the field. We could go to the field with 100 of these bottles filled with indigo disulfonate. We could inject water samples into them. We could track that over time in the field by watching the 610 nanometer absorbance and use that to back calculate the kinetics and the capacity of these systems. There's some data from the injection solution. Now we have to dilute the injection solution down to make it in the right range for the technique, but these are some data where we took that solution and with a final dilution of 4 milligrams per liter, and this is what the degradation kinetics look like. Now if you remember from the previous slide, the calibration slide, which is shown here on the right, the time frame required to reduce all of the indigo disulfonate was about 10 minutes. You can see that here on the right. But in this case, the sulfidated material took about 30 minutes to fully reduce. And that's not too surprising. We would expect some loss of reactivity, but in fact, 30 minutes is still plenty fast for any of the conditions that we're talking about in the field. A more important question will be whether or not it stops the water reaction. The other thing that was probably most surprising about this result is that we would have expected over on the right that the absorption would have gone down from 2.6, say, to about 1 for the case of 4 milligram per liter NZBI. In the case of the field data, it goes down from 2.75 only down to 2.2. So we only get about a third of the reduction in the I2S concentration that we had expected. And it turns out that became then the source of a whole bunch of work that we had to go on and do to try and understand why that number was less than we would have expected. It has to do with the fact that treatment with dithionate oxidizes a whole bunch of the ZBI, more than just on the surface. And so instead of getting a water reaction and indigo disulfonate reaction that we have if we had ZBI, we now have no water reaction, but we have much less capacity to reduce indigo disulfonate because we've converted all of the iron 0 to iron 2, and so there's only 1 electron left for each one of those reactions. So in the end, the answer is that we don't get the capacity from this sulfidated material because we have used up a lot of its capacity in the process of converting the iron 0 to amorphous iron sulfide, and that really is the focus of this second paper and the second example to talk about here. We wanted to go through the process of demonstrating that the sulfidation reaction could be stopped. That the reaction between zero valent iron and water could be stopped by sulfidation, and we wanted to try to find a way in which we could retain as much of the capacity as possible. So I'll go through these quickly because they're a little more complicated to discuss than we have time for, but all of these figures are present in that paper that I just showed you. So if you're interested in application of the sulfidation work, please go to the paper that was in the previous slide, and it'll describe all of this. Again, we can look at the I2S and the rate and the extent to which it's reduced as a measure of the amount of zero valent iron or the reducing capacity that was in that system. And if we look at the sulfide treated cases, we see that there's at least in the case of dithionate treatment, there's a significantly less extent of reaction because, as we said, we've used up a lot of the reducing equivalents in converting all of the iron 0 to iron sulfide. Sodium sulfide treatment, which is the upper right-hand case, is much better in this regard, and that it in effect accomplishes what we hope to do, to coat the surfaces of the nano-DBI particles without using up a lot of the capacity, so we still have a core of iron 0. We can go through with these other two assays to demonstrate that we've accomplished what we hoped. These are the hydrogen data on the left that you've seen before. And when we sulfidate these NZBIs with either sodium sulfide or with sodium dithionite, we see that there is no corrosion that takes place by the water, so we can completely turn off that reaction and essentially save all of the remaining reduced equivalents to reduce the contaminant of concern. The big difference here in the context of the dicyanide is that we have reduced the overall capacity of the ZVI, and that's a problem. So in this particular case, as the paper discusses, treating the sodium sulfite is probably a better choice. TCE degradation, again, behaves as we'd expect. In the untreated NZVI, the reaction stops in a couple of days because the water reaction has consumed all of the ZVI and there's none left to reduce the TCE, whereas the sulfide treatments continue over the course of the reaction. And again, we get better performance from the sodium sulfide treated case than we did from the dicyanide case. The net effect is that sulfidation can completely flip the importance of those two reactions, so that the sulfidated cases, essentially all of the reaction goes through the TCE. The CRPs played an important role in understanding this, but probably the most important part of this is that the CRPs of those three assays we just talked about are the only ones that are readily field deployable. So we could go to the field, we could make these measurements essentially in real time. Summing up then, again, reiterating the points that Paul made, we really need to understand the thermodynamics, the kinetics, and the capacity aspects if, in fact, we're going to understand overall performance. The CRPs provide a rapid screening that we can use either in the field or in the lab. They can work in aqueous phase, which is what the examples I showed here were, or they can work in the solid phase, and they can be used for a whole variety of remediation approaches, both natural attenuation and more engineered solutions. As we look ahead, and that's an important aspect as we start our new SERDP projects, we're going to focus more on the mineral phases. Paul described the need for that in a lot of detail, so I won't bother here. The focus of this new project is going to be on collecting field samples where we can have frozen cores that we can bring back to the lab and work on. They could be done in the field as well, but we're going to do them in the lab. The CRPs will again be used to estimate soil kinetics and try to take advantage of the fact that we can have a correlation between the rates at which those CRPs react and which the contaminants of concern react. And we'll use that to focus on data we need to close sites, and this gets back to the microheterogeneity question, and the coring will let us get at that microheterogeneity. And for those of you who are interested, we have a budget for drilling at a couple of sites, and so if you have a site that's potentially amenable to this, please contact me, and we can discuss that further. The information for our contacts is in the next slide, and with that, I'm happy to stop and answer questions. Thanks.
Great. Thank you so much, Rick. We've received a lot of questions. Can you please start by elaborating on the mechanics of how these chemical probes would be applied in the field and how they could be potentially used to assess the solid phase in the field?
Sure, I can try. Although it's a tough question, and again, it was a topic that it was at the heart of what we did in our past project. A couple of ideas. I mean, one is that you can directly inject those CRPs into the subsurface, let them sit for a while, and extract them in a push-pull kind of a way, and look at how much of the chemical reactivity probe has been reduced, and use that to back out thermodynamics and kinetics and capacity data. That turns out to be relatively difficult to do, and has, as Paul discussed, it only is applicable over modestly narrow ranges of ORP. So you have to know a fair amount about what's going on before you get going. We can also try just injecting those solutions, letting them sit for a while, pulling them back out, and measuring with an electrode in the way that Paul talked about, electron shuttles to improve the quality of those measurements. So both of those are certainly in the realm of possibility, although potentially a little bit difficult to implement. if we're more interested in the kinetics and the capacity measurements, that becomes a little bit easier actually than the thermodynamics. The way we're moving ahead is that if you collect the solid phase in a way that you preserve the geochemistry, like by freezing it in situ before you take it to the surface, if you do it that way, then you have the potential either in the lab or in the field to make measurements on samples that you brought to the surface that can really let you target on specific zones that are of interest. So it's not an issue that we're by any means done with yet. But the short answer is I think it is practical, and certainly as we showed in the field example, you can make those kinetic measurements pretty well.
Great, thank you. Can you please tell us if the kinetics capacity method that you described is ready for practitioner use?
For engineered remediation activities, I think the answer is yes. So if you are injecting reactants and you want to see how far they're being transported or how much of them is being consumed during that transport process, then so that you can make those measurements on water samples because your engineered system is controlling the water chemistry, then it's absolutely ready for practitioner use. If we want to look at natural attenuation or things that take place in low permeability zones, I'd say we still have a bit of work to do. But again, we're actively doing that as part of our new project. So if you've got a site that you want to know the answer to, maybe we can get together and work out a way to use your site as a demonstration and make it happen.
Thank you. Question from Queen's University. With reference to types of redox criteria, if you know the amount of free phase TCE in a laboratory setting, is it possible to estimate what amount of NZVI is required to reduce the TCE?
I'm not sure that I have a very good answer for that. I think in principle, the answer is yes. I mean, I think that one of the great things about the sulfidation work that we've done is that it really helps us focus the reactivity in a real practical sense on the contaminants of concern and not so much on reductant or oxidant demand issues that really complicate those kinds of decisions. So, so one short answer to that is yes. By getting by understanding the capacity issues, we can do a better job of making those kinds of calculations. Of course, that completely ignores the whole transport side. It ignores the heterogeneity side. So there are a whole bunch of other things that make that difficult to do. But I think strictly from the chemical reactant perspective, the probes give us a much better handle on how likely it is or a much better handle on how much reactant we would need to go after a known amount of contaminant. But that's only a small piece of the story of understanding how the remediation effort would work overall.
Thank you, Rick. At this point, I'd like to pull Paul back in. So, Paul, if you could start by answering the following question, and when you're done, Rick, please feel free to weigh in. So, Paul, can you describe in detail how you can go about a natural attenuation assessment using the chemical probes?
In detail.
More detail. How about that?
So I guess I would go back to that response curve figure that I showed towards the beginning of my part of the presentation to really emphasize that's really the unique contribution that we're trying to make here. So insofar as abiotic natural attenuation is the net result of a bunch of background reducing processes that can go on under in situ conditions that we don't fully understand, and we don't have any really practical way of completely deconstructing that system into all of its reducing components and whatever. We can't really do that level of characterization. So you really need a sort of an integrated characterization tool. And so the idea here is that the redox probe is mirroring the behavior of the contaminants. And so you would apply the redox probe. The details of the mechanics of that would a bit along the lines of what Rick was describing. There's different things we could do, but you would apply the probe, and then the result that you get with the probe would parallel the result that you would expect to get with the contaminant. The probe is more sensitive, as in more reactive, than the contaminant. So you can do the probe test quickly under a reasonable testing time scale, whereas you couldn't, because you might say, why not just use the contaminant? But to do TCE by abiotic natural attenuation, you'd have a test that would be way too long. But with Rezazerin, the test is actually quite fast. So those are not specific methodological details about how to implement this, but that's I guess, reiterating the details of how this would work conceptually.
Great. Thank you, Paul. And now for the really important question. Do you have plans to make the chemical probes commercially available in quantities sufficient for large-scale application in the field?
Maybe I'll say a couple quick things, and Rick can follow up. So the probes that we have been emphasizing here are commercially available in the sense that one could get substantial quantities if one needed to. They're not going to ever be dirt cheap, and so we had a long discussion about getting quantities that would be sufficient for push-pull tests, and the answer is probably that's plausible, but it turns on a lot of other issues like the sensitivity of your measurements. So Rezazerin, for example, is fluorescent, and so if you could do the measurements with fluorescence, then you wouldn't need very much, et cetera. So that, yeah, in principle, enough material could be made available, but I think the point that Rick would make is that it would be much better to do the test in such a way that you need so little material that quantities are really not an issue.
And I think just to jump in here, that from the water sample perspective, that is the two examples that I showed in the last few minutes, we're talking about micromolar concentrations of these things and volumes of tens of milliliters per test, and in that context, the cost is just not really even an issue. Does one want to try to implement a large field scale push-pull test in which you do this? I think there are probably a lot of compelling reasons why one wouldn't want to do that in the first place. If I go back to the previous question for just a second, one of the big issues with natural attenuation has to do with what kind of reactions are taking place in low permeability media, where even very slow rates over diffusion timescales could be an important process. Those kinds of measurements and many of the other measurements we're talking about here probably get made better on solid phase samples that are collected and directly analyzed. And if we do that, then again we're back to quantities that are very small. So I think the answer might be that with the exception of someone wanting to do a very large scale push-pull test, probably the quantities are small enough already that the cost is just not even really an issue.
Great, thank you. You both alluded to cost, but specifically compared to conventional methods, can you further elaborate about the cost increases if we were to use the method you developed compared to traditional methods?
Well, I might
talk
jump in
a little bit about the delta?
Well, I might jump in a little bit and say, the cost of the measurements as opposed to the cost of the information you get from those measurements. And so, as Paul clearly laid out in his portion of the presentation, measuring with standard platinum electrodes on water samples that you pull out of a well isn't very predictive in terms of how the system is going to perform. And so those measurements aren't expensive to make, and the chemical reactivity probes are a little more expensive to make, but the information you get from the chemical reactivity probes can be so much more useful that I would probably argue that from a site perspective, you could hardly afford not to do the chemical reactivity probe measurements because they provide you so much more information.
Maybe I can just quickly
would you like to add something?
Just quickly put numbers to the cost calculation there. So, so to make an ORP measurement, you need a pH meter and a platinum electrode. The electrode costs what, $400, and the meter costs $2,000. But you probably already have those things. To buy enough indigo disulfonate or rosazurin to do the kind of stuff Rick described, it's about, I don't know, about $50 a bottle. But you don't already have those things. So the point being that the differences in cost here are not that really the driver. The issue is what information you're getting back.
Yeah, this is really useful. Thank you so much, Paul. Can you please both address the applicability of the probes for ISCO as opposed to ISCR, or in situ chemical reduction, please?
Yeah, well, I'll start with that one. So in the original scope of our project, we framed the whole thing with ISCO in the scope, and we did that explicitly on purpose because everything that we're describing here ought to be applicable in that regime. But we never really, we didn't have the scope and the bandwidth and the resources to really get to it. So we have presented no results here that are directly applicable to that.
Let me just make a couple of comments. One has to do with sort of what we've defined as chemical reactivity probes here. So, for example, in the ISCO world, one frequently wants to measure oxidant demand, and in fact, a standard protocol for measuring oxidant demand is to treat the sediments that you're looking at with permanganate, and you measure the amount of oxidant demand by the amount of permanganate that's consumed. And so in that sense, permanganate is really acting like a chemical reactivity probe to measure capacity. And so we have not developed in the context of this project any of those specific probes to do that. But the concept of using chemical reactivity probes to look at ISCO is not unique. It certainly is not if you define what the probes mean to include things like permanganate. It's an easy colorimetric analysis of the capacity.
Great, thank you both. Another question for you, Rick, and again, Paul, please feel free to weigh in. This is a media-specific question. The approach you described, is it applicable in fractured rock settings, or is it limited to more simple media?
I'm not sure I'd characterize non-fractured as necessarily more simple, but the point of the question is that almost everything in fractured rock is more difficult than it is in porous media. And so, again, from the perspective as the experiments that I talked about, those could be conducted in fractured rock in the same way, and that they're looking at water samples and measuring kinetics and capacity in the same way that they were measured in porous media. So that part of it would be, I think, pretty analogous. Obviously, if you're going to try to deal with the solid phase, you've got the potential for matrix diffusion. You've got all kinds of complicated things that go on trying to get a representative sample of rock. Do you want to get a core and grind it up and make a measurement? How do you want to do that? This is certainly no magic bullet for fractured rock, and we've been giving it a fair amount of thought, but again, it really hasn't been within our bandwidth.
Paul, would you like to add anything?
Well, only that from the chemistry aspect of this CRP response, it doesn't matter. It So it's the difference between fractured rock and porous media is just the mechanics of the application, et cetera, the way Rick was describing, but the probe reactivity part really isn't any different.
Wonderful. Well, thank you both for a great webinar. We appreciate your participation. Our next webinar is on Thursday, September 22nd, and will focus on managing brown tree snakes on the island of Guam using aerial acetaminophen bait. This 2015 ESTCP Project of the Year will feature a fascinating presentation by Dr. Brian Dorff from the USDA National Wildlife Research Center. Registration is open for this webinar, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you could please take a moment of your busy day to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your time.